Okay, I want to talk a little bit about the scientific method and then about problem solving. So both of these things we utilize in chemistry. So the scientific method more so when you're actually observing something and trying to understand what's happening. And then problem solving, either trying to utilize what your results are of these, experiments you do in the scientific method, or just when you're given information, trying to answer a question. Okay, so we're going to look at these two things. So first, the scientific method. The scientific method is an approach we use to try to study what's happening with matter. Okay, so generally, if we're really doing the true scientific method, it starts with observing some phenomena. Okay, so you observe something happening and say, okay, so I see this happens and I think this is why. Okay, and so from that, having these observations and saying, I think this is happening because of this, that's forming your hypothesis. And then you design something to test that hypothesis. So to test, am I right by thinking that this happens because of this? Okay. And so you design some experiment and perform that. Okay. And in the experiment, then this cycle continues. Okay. You do the experiment, and when you do that experiment, you observe again what happens. Maybe, what happens is what you expect to happen, okay, based on your hypothesis. Maybe it isn't. If what happens is what you expected, you generally still don't stop there. You keep going. You usually, do another experiment. You try to test it another way and see, does what I think happen again? Okay. And, you continue that cycle to keep trying to test, is my hypothesis right? Okay. Now, sometimes you do the experiment and it doesn't go like you think. So okay, something's wrong with my hypothesis. And so then you think about it again and you try to propose something new and do more experiments. Okay. So this is something that keeps cycling and cycling and cycling. Okay. And you could break down scientific method in more steps if you wanted to. You can get kind of nitpicky with this stuff, but that's the basic idea of it. And so, you always are observing things, you're testing things, and, you're forming these hypotheses, which are just basically a tentative explanation for what's happening. Now, let's see. Once you do this process, and once it's, you have this hypothesis and the experiments seem to say it's true and it's been thoroughly tested with lots and lots and lots of experiments done typically by multiple people, then eventually it could lead to what we call laws and theories. Okay. Now I give you kind of the technical definitions of these. A law describes the way nature operates under a specific set of conditions, whereas a theory explains why nature behaves the way it does. Sometimes it's helpful to think of it a little bit different. I would say, a law typically is something more mathematical. So a lot of laws have some sort of equation related to them, or you can kind of make an equation that relates to them. So it's a little more definite. So if you're under this same set of conditions, then this law should tell you that this should be what you see. Okay, this definitely should be what you see. Whereas a theory is just trying to explain why you're seeing this, not trying to, give you a mathematical answer or anything like that. It's trying to explain why. whereas the law is trying to direct you to what you should be seeing. And like I said, usually the laws tend to have some mathematical relationship related to them, whereas your theories usually are just a list of these are kind of the bullet points of it, what's happening or what you see. Okay. Now, the scientific method is something that is applied usually in the lab. Okay. Now, at the level of like an introductory and a general chemistry course, you usually don't go through this whole cycle. You definitely don't go to the point of developing laws and theories. But usually it's a little more guided. Usually you come in and start at the experiment stage instead of observing something and trying to come up with a hypothesis. But overall, it's still that same cycle. And you're just trying to observe something and understand what's happening by actually doing something, okay? Whereas in like a chemistry type lecture, a lot of times instead of having you do experiments and observe things and stuff to understand something, to kind of speed things up, you're just given a scenario. You're given the information and you're told that this is what we know and this is what we see. Now answer this question. Okay. And so that you don't tackle using the scientific method. So the scientific method is something when you're actually actively going in and doing some experiments, actively observing things. But there's a good chunk of chemistry that's also a little more, initially you're not active in the process. You're just given this scenario and asked to solve it. Now, in that case, you want to take more of a definite pathway or more of a systematic approach to this in a mathematical. Okay, so scientific method's good to understand. It's good to understand this process because that helps you tackle things when you don't have necessarily someone just telling you a bunch of information. When you're just trying to start to understand something or discover something, use scientific method. Okay, but if you're given a problem, you want to use some sort of problem solving strategy. And I'm going to give you one that I would suggest for chemistry problems. You can follow a different strategy, that's fine, but this is a good way to go about it. And so break it down into just a few steps here. So I would say, you're going to identify your starting point. Okay, and when I say your starting point, that means what's given. Okay, because something that's given must be where you start. Okay, so if you're doing math, you can't start with something if you don't have it, right? So you have to have some information to start with. And so you look for numeric values in the problem, make sure you write down their units, you look for any chemical formulas or possibly names of compounds that then you can write chemical formulas for, any reactions given, or even if it's explained in words. So that kind of stuff is going to be useful. And you read out all the extra words, okay? And then you look for what's your ending point. And your ending point is what are you looking for? So what are they asking for? And not only consider that they're asking for, say, a density, but are they asking for a specific unit? Or if they're not asking for a specific unit, what would be a possible valid unit? Some possible valid units. You should at least be aware of that. Once you have those things kind of written down, you need to think about how am I going to connect those? Look at that information and think about, is there enough there already? There's a definite connection between those? Or does it seem like I'm missing steps? Am I missing some information? And if so, you need to think about, can I look that up? So a lot of times, you might need some unit conversions that you're not given. Okay, and you can look those up. Or maybe you need an equation okay? And that you can look up as well, okay? And so list other things that you think might be useful, okay? And then, put it all together, okay? Solve the problem. Whether you approach it as dimensional analysis or as kind of a plug and chug. So if you have an equation that definitely relates these two things, you can use the equation and just plug in information and solve for the unknown, okay? Or you can kind of tackle it unit-wise. So you start with something that's given and you convert units until you get to the unit you want, okay? Using dimensional analysis. Okay, a lot of times that'll lead the way in chemistry. Now, once you do that, be sure you check your answer. And when I say check your answer, it doesn't always mean what you think it means. It doesn't necessarily mean like check is your answer right, because you may not have access to that, right? But when I say check your answer, I mean, think about, is it, a good chance that I'm right, or at least very close to on the right track. So look at the units. That's one dead giveaway. If you go through, when you do the math, you need to have units in your work and then check what cancels and what are you left with. If you solve the problem and you come out with milliliters and you were asked for a mass, it can't possibly be right, because milliliters is a volume unit, not a mass unit, okay? Then also think about, did I give the correct sig figs? Meaning go back and look at your work, consider sig figs or uncertainty in your values, and determine how many you should have in the end, and make sure you rounded. Okay? And then think about, does it make sense? This is the part of checking your answer that you may or may not be able to do. Some things, you get a number and you're like, that's way too big. That definitely is. I know it is. And other times you're like, I have no idea if this should be big, if it should be small, if it should be around this value. And, if you have no idea, then you have to trust that you did these other steps and you did them properly. They probably good. Okay. But sometimes some things are going to definitely make sense or not make sense. Okay. And don't ignore that. And so if you follow this or some other kind of very logical stepwise process to solving problems, you should be able to do pretty good in chemistry, or at least on the mathematical stuff. So let's do a few examples, going through this type of process. So the first one, I say, what is the mass of a 0.780 meter cubed block of NaCl in kilograms? And I give you the density of NaCl in parentheses there. So I'm going to list what I'm given. So what I'm given is 0.780 meters cubed. And it can be helpful if you label what that is. So I'm going to label that that's a volume. Okay. And then I'm given the density, right? So I'm pulling out these numeric values. Grams per cubic centimeter. Oops, lost my centi. There we go. You can also write down that it's NaCl. Sometimes that's useful, what substance it is. Sometimes you don't really need it. But okay, I have that stuff. And then what am I looking for? Well, I'm looking for the mass, right? And I specifically want that mass in kilograms, okay? And then, let's see. I have mass, that's what I'm looking for. I have volume and density. And so if I think about how those things are linked, well, there is an equation, density equals mass over volume. I can use that, okay? Now, alternatively, you could just tackle it based on units. You could say, well, I have really meters cubed if we focus on the standalone unit. And I want to go to kilograms, and I have a conversion factor of grams per cubic centimeter. Well, I can eventually link those, but it's gonna need some extra conversions. So density equals mass over volume isn't quite gonna be enough, okay? Because I have meters cubed and centimeters cubed, right? And so I need to be able to relate those. And so you should know that a meter equals 100 centimeters. Okay. And if you were to cube this stuff, so if you were to cube this and cube this, then it would give you that relationship between meters cubed and centimeters cubed. Okay. And then you could look at, well, I have something in grams and I want it in kilograms. So you could say, well, I know the relationship between grams and kilograms. A kilogram's bigger, so 1 kilogram should be 10 to the third grams. Okay, so those are some extra pieces that you may not notice before you start trying to solve the problem, but eventually you should notice that you need that stuff. Okay, so all of that stuff then we should be able to put together and solve for mass. Okay, which if you want to use this equation, then it'd be helpful if you rearrange it. So mass would be equal to density times volume. Okay. And so we can simply plug into that, or we can do dimensional analysis. If you plug into that, you need to be careful. Okay, so if I plug into that equation, that's where sometimes people forget this other stuff. So if you say density, oops, not density, I want to use the rearranged form of the equation. Okay, so let's use that. Density, no, I'm still doing, going back to the initial, I'm going to use the rearranged. So mass, sorry, equals density equals, oh, and does want to work. Mass equals density times volume. There we go. Then that would be 2.165 grams per cubic centimeters times 0.780 meters cubed. But if you just blindly plug that into your calculator, it would come out wrong because those units don't cancel. You would come out with something in grams times meters cubed divided by centimeters cubed, which is a senseless unit. Okay. And so you would need to add in these extra conversions. You need to find a way to add those into them. Okay. And so basically, when you're doing that, you're doing dimensional analysis. So I would actually just start off doing dimensional analysis. So I would start with the given information. And since you have two kind of numbers given, the volume and the density, it's usually easiest to start with the one that only has one unit. So not the fraction, because you don't know which way the fraction needs to go. So I would start with the 0.780 meters cubed and then say, okay, well, what can I convert meters cubed to? Well, meters cubed, I can convert to centimeters cubed by using this relationship. Oh, that one, sorry. 1 meter is 100 centimeters, right? And we want this cubed. And so that's going to cancel my meters cubed to give me centimeters cubed. And then you say, okay, well, what can I convert centimeters cubed to? Well, I can convert centimeters cubed to grams using the density. And so there's 2.165 grams per 1 cubic centimeter. Okay? And then I can convert grams to kilograms by using that conversion. 1 kilogram is 10 to the third grams. Okay, and so that should go through and cancel my meters cubed, my centimeters cubed, grams, and give me kilograms, which is what was asked for. Okay, so always make sure you're paying attention to not only that we're asking for a mass, but also what unit is it asked for in, because sometimes that's specified. So if I do that, the 0.780 times 100 cubed times 2.165, and then divided by 10 to the third. And it looks like, well, what the calculator gives me is 1688.7 kilograms. But then you got to go back and think about sig figs. Okay, so pay attention to sig figs. Here, you've got 3 sig figs. Oops. No, this thing is not cooperating right now. Try this again here. So here we go. We've got 3 sig figs. And then this conversion, that's exact. That has infinite sig figs. Okay? Metric prefix conversions are all exact. And then our density, this is 4 sig figs. And then the symmetric conversion, that's infinite. So 3 sig figs is my limiting factor. So I have the 1, the 6, and this first 8. I look to the right and there's an 8, so I'm going to round that up. So it is 1690. I need to change that to a 0 to keep my decimal place in the appropriate location. Kilograms. Okay, so that's my answer. Or if you don't want to write that 0 because it makes it look like, I guess to some people, 4 sig figs, then you can write 1.69 times 10 to the third kilograms, and that is also acceptable. Both are correct. This one in scientific notation is more clear to people how many sig figs it has. Okay. Okay. So that is one example. Let's look at one more example. Doing some problem solving by kind of focusing on the units of things and kind of this basic problem solving strategy. So what I'm going to do is go through this problem and pull out the information as I read it. So we have toilets account for a high percentage of daily water use in the home. Now, there's nothing in that first sentence that I think is useful mathematically, so I'm going to keep going. A low-flow toilet uses 1.6 gallons of water per flush. Now, that should be helpful. Now, that is ratio, 1.6 gallons per flush. Okay, so I'm going to write that as a unit factor. 1.6 gallons per flush. Okay, now you could write this the other way around, upside down. Okay, it doesn't matter. We can always flip it later. And then it says, and a family of 3 averages 15 toilet flushes per day. Okay, so a family of 3, I'm going to skip that at the moment and just say 15 toilet flushes per day. Okay, because that's definitely another kind of conversion factor. So 15 flushes per 1 day. Okay. And then it says, how many cubic meters of water will a family of 3 use for flushing the toilet every year? Okay. And then there's another unit relationship. This 1 quart is equal to 946 centimeters cubed. Okay. And those other things I skipped are kind of related to what's being looked for. So how many cubic meters of water family use for flushing the toilet every year. So cubic meters, that's, oops, cubic meters, that's what I'm looking for. That's not a very good 3. So how many cubic meters of water? Well, a family of 3, so that's what this other stuff related to, a family of 3, so I'll ignore that and not write that down. For flushing the toilet every year. So it's meters cubed is what I'm looking for every year. So for 1 year, okay. Or I guess I can write that as a ratio too, meters cubed per 1 year, okay. And then let's see. Now we need to think about how can we relate this stuff. Well, it's all a bunch of units and ratios, okay. So what I should look for is, well, let's focus on the units, what we have and what we're looking for. Well, we're looking for meters cubed. Well, out of the stuff given, we don't have meters cubed, we have centimeters cubed. So again, it'd be helpful to remember that 1 meter is 100 centimeters, and that if we cube that, that's the relationship we need to link those two things, okay? Once we're there, we have, let's see, quarts. We don't have quarts in anything else. And so then, well, the other volume thing we have is gallons. So how can we relate quarts and gallons? Well, there's 4 quarts in a gallon. That's something you can look up. Okay, and so that would be useful. That would link those two ratios. And then flushes can directly relate to this other ratio. And then we have days. And I need to kind of tie days to years, okay? And so you could say there's 365 days in 1 year. Or if you want to get really, really technical, you could say there's 365.25 days in a year. You really want to, if you consider leap years. I'll just leave it as 365 days per year, okay? And so we have all of those relationships that can help us get to our end goal, okay? So we want to know how many cubic meters per year, okay? You can, well, what I would do is really, I'd say, well, this 1 year I know, I want to deal with 1 year. So I would start with 1 year, okay? Otherwise, I would look at, okay, I'm looking for meters cubed, so I want that on the top. So I would take this ratio and flip it and start with that. So one way or another, I would start with 1 year and say, I just want to talk about in 1 year. So in 1 year, what can I convert a year to? Well, I can convert a year to a day. So that's this relationship over here, right? And so there's 365. This thing's not behaving. 365 days in 1 year. Okay. And then I can relate days to flushes. So that's up here, right? That's here. So well, I started with the year because that was a value I knew. And I converted days to years, or years to days, sorry. And then I can convert days to flushes. Okay, so 15 for 1 day. And then I can convert flushes to gallons. So there's 1.6 gallons per flush. And I can convert gallons to quarts. So there's 4 quarts in a gallon. And I can convert quarts to cubic centimeters. Oops, I'm going to run out of space because I wrote way too big. And so it's 946. I'm writing the numbers in the wrong place. For 1 quart. And then 100 centimeters in 1 meter. And I need to make sure to cube that relationship, right? And that should go through and cancel things and give me what I want, right? So in a year, convert that to days, convert the days to flushes, the flushes to gallons, the gallons to quarts, and the quarts to cubic centimeters to meters cubed. So if I punch that all in the calculator, that's going to tell me how many meters cubed in 1 year. Okay. So 1 times 365 times 15 times 1.6 times 4 times 9.6 divided by 100 cubed. So it looks like I get from the calculator 33.14784 meters cubed. Okay. And so with that, analyze sig figs. Okay. So we look at this and we say, okay, 1 year, we're talking about exactly. Okay. And so 365 days in a year, that's exact. Okay. 15 flushes in a day. That's not going to be an exact. This family doesn't do that. That's an approximate. And so that's going to be a 2 sig fig. Okay, the 1.6 gallons per flush, that's also something that's measured. And so that is going to be 2 sig figs. Okay, 4 quarts in a gallon, that's a definition. So that's exact. So that's infinite. 946 cubic centimeters in a quart, that is a metric system to an English. So that is not exact. That's 2 sig figs. The meter in 100 centimeters, that is exact. That's a definition. And so 2 sig figs is our limiting factor. So we have 3, and then the 3, we look to the right, that 1, we don't do anything. So it's 33 meters cubed would be our answer there. Okay, would be how many meters cubed per year based on that information. So I know that was kind of an obscure example. It's not really a chemistry example, but that gives you an idea of how to kind of analyze the units. Now, you could have started in a different way than I did and come out with the same answer. In the end, you would have to somehow do all of those steps, okay? Somehow put all that information together in the same way, but you could do it in a different way. And so focus on the units. You wouldn't have to read this problem and say, oh, I know I need to multiply this and divide by this. No, you don't just know off the top of your head. You let the units guide you, and that will help you through chemistry.